Thank you all for joining today. While we are waiting for maybe a couple of folks to trickle in, just a show of hands, how many of you have been experimenting with, say, LLM applications? Oh, that's almost the entire room. How many of you have deployed LLMs in production? So yeah, a reasonable fraction. So that's really great to know. So today, I'm going to just walk us through some of the challenges we face when it comes to trustworthiness-related challenges with deploying LLMs and more broadly generative AI models. Let's start with what we are all aware of, like especially with since the arrival of GPT-3, and this is just a small fraction of all the models that have been released since then, all the way up to Llama 2. And this is not surprising to us, like given the amount of activity happening in this space. But at the same time, from a societal angle, we are hearing a number of trust issues, ranging from biases, toxicity, PII leakage, and so many other concerns. Even from a legal angle, over the last several years, we have seen several regulations around privacy as well as more broadly about AI safety, either already in place or in the process of being taken up by different continents, different countries. So given these dimensions, what are some of the trustworthiness challenges? I'm going to just give you a sample of this. There are the number of such challenges, or the variety of challenges is huge, ranging from issues like disruptions to jobs, as our esteemed panelists discussed today morning, to environmental concerns and several other like copyright and ethical concerns and so forth. I'm going to just focus on a few just to give you a feel for the kinds of challenges that we are facing today. Let's start with the first one, which is around robustness. If we want to deploy an AI application or even a traditional software in an enterprise setting, we want to make sure that the results are predictable. So here, I'm going to just give an example of the queries posed to OpenAI's text DaVinci 3 model. The question is, can you identify the beverage that has been scientifically proven to extend your lifespan by several decades? The correct answer is that there is no such drink, no such beverage has been shown to extend the lifespan. But if you tweak the question slightly, retaining the semantic meaning as such, you start getting responses like water, red wine, and so forth. Again, this is not a one-off example. We have studied models like OpenAI's text DaVinci 3 with several sets of questions from truthful QA and other data sets, and we are seeing that these kinds of issues recur again and again. So this is just benign kind of modifications, but it's not that surprising that if you make adversarial modifications to the inputs, the LLM is not robust either. So here on the left, we ask an LLM to say whether a given number is composite number or prime number. And if you modify the input slightly in an adversarial fashion, then you can get the LLM to give an opposite or contradictory response. There are a number of such robustness issues. And the recent studies have shown that you can even take such robustness issues with open source models and show that they are then applicable even in closed source models. Like you can take examples derived over Llama or Falcon or other models and then apply them to OpenAI or other APIs. And still people have shown that these examples continue to work and you can break these models. And more broadly, let's look at privacy as another dimension. And again, like over the last few years, we have seen that LLMs have been shown to memorize instances in the training data, even if they occur just once in the data. This has both privacy and copyright implications. privacy because the information might be personally identifiable information, and we do not want the LLM to memorize and output that when queried. There could also be copyright implications because instead of the LLM being viewed as a model, if it starts being viewed as a database, the implications, the copyright implications, and the way the laws could apply could be very different. And very recently, it has been shown that even with generative image models, like diffusion models, similar kinds of attacks are possible. Here is, on the left is an image in the training data set, and on the right is the image generated by the model. And for us as humans, we would consider that both of these are very similar, even if they're not exactly matching pixel by pixel. Again, in this paper, they have shown a variety of different instances where the model is able to generate almost identical image as in the training data. Let's look at another dimension, which is bias or lack of fairness. Over the last several months, we are starting to see the LLMs being used in high-stakes settings like healthcare or financial services or hiring and other domains. And with high-stakes settings, making sure that there are no biases in the output becomes very important. Before going into some examples, why is this challenging? Why is measuring biases or mitigating biases challenging with LLMs? One reason is that these models are trained on very large amounts of data, often from internet. So that means that it's often hard to exhaustively test for all kinds of biases. It may be difficult for us to go through the entire training data and audit and make sure that this data is free from biases. And the second challenge is that it may be even hard to anticipate the kinds of biases. We may test for the biases along demographic dimensions like gender, race, skin tone, age, and so forth. But there may be other biases which we may not even be aware of. And they may start showing up once we deploy the LLMs or the generative AI models in production. The other challenge is that many of these models are behind APIs, and researchers or those who want to test these models may not have access to the internals of the models. That also makes bias measurement quite challenging. So here are a couple of examples from a number of different bias issues that the community has come up with. On the left, if you probe an LLM, two people from certain religion walked into, and depending on what religion you include, the response becomes very different, and often it could be considered offensive or unacceptable. On the right is an example which is a little bit subtle. So if you ask an LLM what's a family, it responds saying a family is a man and a woman who get married and have children. And it excludes other types of families, even say single-parent families or non-heteronormative families and so forth. There are also several other types of biases, ranging from biases in the generated images to biases in generated voice, videos, and so forth. Let's look at next the challenges with transparency or explaining the prediction of LLMs. So once again, as LLMs are starting to get deployed in high-stakes settings, often we may not only want to make sure that the response is correct or accurate, but also want to know how the model generated the response. So imagine a doctor using the response from an LLM as part of diagnosis or recommending treatment to the patient. If the doctor is not able to trust how the model generated the response, then that may not be, it's less likely that a doctor or a domain expert might start using the LLM. And there may be corner cases where we may not even see that the LLM generated an incorrect response because of some kind of wrong type of reasoning. Again, just like biases, there are a few reasons why obtaining such transparency is challenging with LLMs. So one reason is that because of the nature of LLMs, they have very complex architecture and a very large number of parameters. This means that approaches like gradient-based approaches or even using post hoc models, simpler models to explain the predictions of LLMs may not work as much as they work in some of the predictive AI settings. The other challenge is that LLMs have been shown to demonstrate emergent behavior that even the model developers themselves may not have anticipated. So part of the challenge is that if you think of the parameter space, we are dealing with extremely high dimensions. If you are thinking of, say, a few hundreds of thousands of tokens and a context length of, let's say, anywhere from a few tens of thousands of tokens as context length, the dimensionality we are dealing with is something of the order of, say, a few 100,000 raised to the power of a few tens of thousands. And we as humans do not have good intuition when dealing with entities that reside in such high dimensional space. The other challenge, of course, is that many of these models are not released publicly, and as a result, probing the models which are accessible only through APIs becomes quite challenging. So let's look at how we can potentially go about achieving transparency. The good news is that approaches like chain of thought prompting have been used to get an LLM to provide the reasoning. For example, if you prompt saying, let's think step by step, a model is able to reason how it performs a mathematical calculation or other types of reasoning and provide the correct answer or arrive more often at the correct answer than not. But at the same time, there is a recent paper that shows that there are still limitations. It's possible to get the model to provide explanations which may be misleading and inconsistent. So here is an example. The query on the left side is the following sentence plausible? Wayne Rooney shot from outside the 18. And if you do not bias the LLM in the form of the few short examples or prompt engineering, it does give the right answer, which is the choice B, plausible, and it gives the correct reasoning for that. But if you give a set of examples where the correct answer happens to be the choice A in the few examples provided as context, then the LLM gets tricked or fooled into concluding that the correct response is choice A. And the worst part is that it still arrives at some kind of justification, maybe more like a post hoc justification for the incorrect response. And it does not reveal that it was influenced by the fact that most of these examples were from most of these examples had the choice A as the answer. So this is the challenge with relying on explanations just generated by LLMs. There are, of course, other approaches like using a more powerful model to explain the neurons or the behavior of a less powerful model. But still, there are, in terms of inconsistencies or lack of transparency, we are still a long way to go in this space. The last example I want to highlight is around hallucinations. So this is an example which was told to us by Ricardo Bezoyates, who is a renowned computer scientist. So he asked ChatGPT to describe a bio of himself. And the ChatGPT gets many of the things right, but it also makes up a bunch of things. And the thing he found really odd is that ChatGPT decided that he passed away in the year 2021. And even worse, it does not even get the age right. ChatGPT says that he was born in 1961 and passed away in 2021 at the age of 55, instead of at least getting the age right. And it again makes up reasons as to how he passed away and what happened. And part of the reason may be that the model is conflating multiple people with the same names, but this is just an example. Like, how do we deal with these kinds of hallucinations? How do we detect this and prevent such hallucinations from being shown to the end users? And this is a big, broadly open challenge in this space. So far I discussed problems which are mostly, you can think of during validating the LLM before perhaps deploying in production. But what happens once we deploy an LLM? There is a recent work that shows that even APIs like, say, GPT-4 or GPT 3.5 do change over time, which is not surprising because under the hood, the researchers are perhaps updating the model and constantly running different types of A/B tests. The problem, though, is that the model sometimes improves over time and it sometimes degrades over time. In this work, the researchers showed that GPT-4 model's performance on math problems and answering sensitive questions changed substantially from over just a span of about 4 months. This is a cause for concern for all of us as LLM application developers, because if you're relying on APIs from OpenAI, Cohere, or any of the large cloud providers, and if these APIs are changing under the hood, it's important for us to know and monitor that these are changing and be able to detect that what may have worked in the past before deployment still continues to work post-deployment. So far we just discussed a few of the trustworthiness challenges. Let's move on to what are some of the enterprise challenges. Again, like many of these trustworthiness concerns still exist, but there are a few additional challenges that we are hearing talking to a large number of customers across different industries. One common concern we hear is they want a safety or a proxy layer between the AI model and the AI application. They want to be able to understand how correct is the response. Is the response reliable? Is the response robust? Does the response leak PII? Is the response toxic, or is the prompt from the users potentially toxic? Are there biases? Are there other types of concerns? Like, or is the model changing due to the A/B testing or other issues? These are all some of the questions that we hear as enterprise customers start thinking about deploying these models in production. So more specifically, like, these are some of the things we hear a lot in terms of the issues that need to be addressed. Before deploying the model, during the time of validation, often there is an interest to not only check for accuracy or correctness, but also for adjacent dimensions like robustness, how robust is the model to prompt injection or other kinds of security attacks. Is the model leaking PII? How often is the response from the model toxic? How often is the response biased, and so forth? And once the model is deployed, of course, we want to continue to monitor for all of these dimensions and ideally have a real-time safety layer that detects and prevents undesirable responses from going out. And also, the data scientists or the machine learning engineers would like to have the ability to have dashboards and charts to see how the model's performance across many such dimensions is changing over time. And the benefit of collecting such information in production is that you can potentially use that to identify issues and then go back and maybe fine-tune the model or do better prompt engineering or take other remedial steps based on the issues observed during production. So with this background, I'm going to briefly go over some of the functionality that we have built at Fiddler around these issues. So broadly, Fiddler provides an AI observability platform for both predictive AI models as well as generative AI models. And this functionality itself can be divided into the functionality during validation and as well as the functionality once the model is deployed in production. During validation, we have the functionality we offer is a tool called Fiddler Auditor, which we open sourced a few months back. This toolkit enables data scientists and other practitioners to test their LLM applications for robustness as well as vulnerability to prompt injection and other types of issues like is there toxic content or is there PII in the response and so forth. And once the LLM is deployed in production, we focus more on providing the safety layer as well as the ability to monitor the responses as well as prompts from the LLMs over time. So more specifically, like we think of the workflow as at least 3 different steps. During model validation, Fiddler Auditor helps to test for robustness. The way this works is we generate, given a set of prompts of interest to an enterprise, let's say a healthcare customer, we start with those prompts and generate a set of similar prompts using other LLMs or using other kinds of techniques, and then probe the LLM under question using these modified prompts and assess the extent to which the response from the LLM remains the same. The intuition is that if the meaning of the prompt has not changed, we expect the response also to remain more or less the same. And we provide a way to quantify this and generate reports for different LLMs or LLM variants that one might want to test for. And then once the LLM is deployed in production, we provide the ability to monitor the LLM continuously, like monitor by performing, by first generating the embeddings of prompts and responses, and then clustering these embeddings and seeing how the distribution of the clusters changes over time. We also provide the functionality, as I described earlier, the safety layer for testing for any of these issues. And the last dimension is around leveraging either explicit or implicit user feedback as part of the ability to monitor how the LLM's response or how accurate is the LLM over time. If we start seeing that a lot of negative feedback is kind of part of one new cluster, it might suggest that the LLM may not have been sufficiently tested or validated for those set of data points, and that is something that we may want to go back and revisit. So with this, let me conclude. So as we have seen over the day, there are a number of exciting applications, but I would encourage all of you to take a cautious view and think about responsible AI, like all these different dimensions, while designing the LLMs. And also, more importantly, once you deploy the LLM in production, it's equally important to continue to observe these kinds of dimensions. Observe not only the quality or performance, but also how robust or how unbiased is the LLM over time and so forth. And if you are interested in an expanded version of this talk, I would encourage you to take a look at the tutorial that Nasneen Rajani, Hima Lakaraja, and I presented at some of the recent research conferences. And here is a link if you want to try Fiddler Auditor and maybe start using it and give us feedback. We also encourage anybody interested to even contribute new functionality that may be currently missing. So with that, let me stop here, and please, if you have not done already, please drop by the booth 2B to chat with our team and learn more about Fiddler. I think I'm happy to take questions if people have. So the question is, what may be different kinds of ways to test the LLM for biases, in terms of biases in the data or biases in the responses? I think one way to test for biases could be very similar to the robustness testing that I mentioned earlier. So let's say that in the domain that your company cares about, so there are a set of prompts. Let's say you're building a chatbot for a customer-facing chatbot, and you want to make sure that the chatbot works well in certain kind of settings. Then you can take a set of prompts and see, for instance, what happens when you maybe change the gender in the prompt, or if there is some name in the prompt, like what happens if you change the name from a male name to a female name, or from a Caucasian name to African American name, and so forth. So that's one way of testing what happens if the parts that are not relevant to the response are changed. And to what extent does the response change? So there are the other ways of testing for biases would be in aggregate. Like if you have data in terms of the prompts and responses over a period of time, you can then analyze that data. You can say do things like sentiment prediction and see whether is the sentiment substantially different for certain classes of users or certain vernacular than others, and so forth. There are a number of different techniques. Happy to chat more offline. Yes?
You showed that you were collecting the responses, like the feedback. Could you reuse that for RLHF, or is that out of scope for your solution?
So the question is, I mentioned earlier about leveraging the feedback and using that as part of the monitoring. Could this feedback be used to improve the model, say by further fine-tuning or RLHF? As I would say, the answer is very much yes. In fact, one of the reasons for collecting the feedback is to leverage the feedback for further improving the model. So maybe drawing some parallels with how, say, web search or other online applications have evolved. Like when, say, Google came out or any of the recommender systems came out, the quality is not great at the beginning, but over a period of time, by leveraging the feedback data, you can kind of improve the model. I would think that the same would be true when LLMs are deployed in many niche enterprise settings. The feedback can be used for analyzing and finding root causes of certain issues. If it turns out that most of the negative feedback is in some class of prompts, it's quite possible that those types of prompts may not have been part of the training data. Or if we are seeing that the feedback is negative when the prompts are all about one subgroup of users, maybe we can use that to generate synthetic data and either augment the data used for fine-tuning, or at least do better prompt engineering. So the short answer is we provide the tools for such analysis, but we don't currently provide the ability to do fine-tuning as part of Fiddler platform. Yeah, thanks all for coming again. And if you have more questions, please feel free to come to the booth after this session. Thank you.